The lesson for today, is work and energy. Work and energy are not new words to you. In theory, they came up way back in elementary school. And although you may have felt good about them in elementary school, traditionally, by the time people get to high school and even beyond into university, it turns out that sometimes it didn't really click. And what people thought they knew about energy isn't actually correct about energy. By the time you're watching this video, you should have already done this. You should have opened that other document and done your own little thinking and reflecting on what work and energy are. If you haven't done that yet, take a pause from this one and go look at that. It'll just help. It gets you thinking about equations and what the words mean and a little bit of other things. So make sure you've got that done first. One thing I want to point out, so read through this text, but I'll talk you through it as well. But one thing I want to point out is when you Google those definitions for work and energy, they're kind of circular. Typically, when you Google it, when you Google work means, work often means having pushed something around or made it move or changed the energy of something. And if you Google what energy is, it usually says something like the ability to do work. So work is when you've caused something to gain energy. Energy is when something has the ability to do work. So they kind of flip-flop back and forth. And you'll notice later in this, on purpose, I'll make up questions using the word energy, but then you'll use an equation connected to work. Or I'll make up a question that says find the work to blah, 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 blah. But to answer that question, you actually use an energy equation. That's because of the circle. Energy and work, in a way, they're kind of physics synonyms. They represent the same sort of quantity. More on that later. Going to start off with thinking about work first. One of the definitions of physics, of work in physics, we say you've done work if you push something with a force and that force has made the object move. So there's two things going on there. Work involves a force that makes something move. Let's say, for example, you had like the world's worst summer job and all you had to do for your summer job was stand outside and make sure a wall didn't fall over. So all day long you stood out in the sun and you pushed really hard on a wall. Just stood there all day long in the sun, pushing on a wall to make sure it didn't fall. If the wall never moves, even though at the end of the day you'd probably be exhausted after being outside pushing on this wall all day, according to physics, since there was a force, but there was no motion, no movement means no work. So even if you do that all day long, no work is done. Or maybe another crappy summer job you got is you're standing outside and you just have to hold something. You don't lift it, you don't set it down, you just stand there holding on to something. You're pushing upward on it, so there's definitely a force on it, but if it doesn't move up or down, then same idea. No movement, no work. So to do work requires two things, a force and some motion. And then what we're going to get to in a little bit is if you do work, then the object you do work on is going to have gained energy. Now here we go right here. So work means force and motion, and work also means increasing the energy of the thing you did work on. To make sense of this, to wrap our brains around this, let's consider a forklift. So there's my little picture, a funky looking forklift. But let's say, I don't think forklifts really work this way. I'm not a forklift expert, but let's say that our forklift has two motor systems. It's got one motor, one system dedicated to lifting, and it's got another one dedicated to the driving. They're completely independent. One motor system takes care of the up and the down, and the other motor system is connected to the wheels and actually moves it around. Let's say the forklift, in the course of doing its job, picks up something, drives it across a warehouse or a parking lot like that picture there, and then it lowers that thing again. In the first part, when it's lifting the load, then it's the lifting motors that are doing the work. Whatever it's lifted has got more energy after being lifted than it did before. So if it lifts this heavy thing up, once it's lifted, that thing has more energy. It's got more energy. The energy is related to the changing height, so we call it gravitational field energy, or sometimes I'll call it gravitational potential energy. Field energy is a more generic word that we'll use again in grade 12, and university profs use it. The higher you lift it, that means you've done more and more work on it. That means the object has more and more gravitational energy, because the work done, where'd it go? The work done is equal to the energy gained. This kind of thing in here. When the forklift starts to drive around, the lifting motors aren't actually doing anything. They're keeping it at the same height, but the driving motors are now doing some work. When the forklift is moving, it actually has more energy than when the forklift is stationary. This energy related to motion is called kinetic energy. The faster something is moving, the more kinetic energy it has. When I teach this in person and I can actually talk to people about it, a common theme is in elementary school, kinetic energy gets related to wind. That's how a windmill can spin. It took work to get the forklift moving. The work done to get it moving, we say, is represented by the kinetic energy that the forklift has. Now, a weird one, when lowering the load, this doesn't always come up in elementary school. When lowering the load, again, we're back to the lifting motors, but they're not actually doing any real work. In a way, they're taking energy away from the load. When the load was way up high, it had a lot of energy, well, more energy, and as it lowers it, then it actually has less energy at the bottom. So the load had more energy when it was up high than it did when it was lower. Sometimes we'll do questions and we'll say that negative work was done. Negative work means our system took energy away from the thing we did the work on. A classic case like this, like lowering something heavy, it'll have less energy when it's down low than when it was up high. In a case of negative work, a clever engineer could figure out how to get the energy back. If you're into hybrid cars or electric cars, they've got something called regenerative braking. That's a system that a clever engineer, clever physicist came up with to get the energy of braking back into the batteries. I want you to think about this before I talk about it, but what if? What if our forklift with two systems, what if the driving around part was done by gas and the lifting part was done by battery? So they're completely separate. Not only are they separate, they're separate energy sources. Gas is used for the driving, a battery is used for the lifting. What if our forklift drove around all day long without actually lifting anything? What would happen to its battery level and gas tank? I don't know why a forklift wouldn't lift anything, but let's just say for the job that needed to be done, it just literally drove across the warehouse all day long, but didn't actually ever lift or lower anything. What if, different scenario, what if the exact opposite? What if it never drove anywhere, but just lifted things up, and then someone took them off, and then it lifted another heavy thing up over and over again? What would that do to it? Oops. If gas is for driving, then if it drove all day without ever lifting anything, it would run out of gas. Well, let's not say run out, let's just say use gas. You would need to get that sort of energy that's related to its kinetic. When it lifted, that's the other system, that's the battery system, so it would wear out or use up the battery. And of course, if it did a mixture, if it drove and lifted, then it would use some of each. Thinking about that, hopefully you can kind of separate in your brain that the energy of motion is a little bit different than the energy of lifting. We'll come back to that a little bit later, next lesson. So bottom line is, I've said it out loud, but I'm typing it here. Work done is kind of related to the energy gained. We'll see that next. In the examples that I give you to do next, sometimes I'll say the word work. I think we'll get to the examples in a bit. Sometimes I say the word energy. You'll just have to think about what's given and what equation works best. That'll make sense as we start doing questions. All right, Cruising right along. When I asked you to answer those questions at the top of this, one of the things was to find the equation for work. This is our equation for work. It's the force multiplied by the displacement. Force from last unit, push or pull, displacement from the unit before, the overall change in position. If we short form it, the short form for work is going to be capital W. We saw the short form for force and displacement before, F for force and D for displacement. I was a little bit lazy when I typed it. Work is definitely capital W. Force is a vector, so if we're being really strict, should have that vector hat. Dot as our multiplier. Displacement, again, should have a vector hat. Unit-wise, the force is going to be in newtons. The displacement is going to be in meters. It wouldn't be wrong to call them Newton meters, but historically they get called joules. Really cool story about an old white guy physicist named James Prescott Joule. Not only old and white, but rich old white guy. Basically, his dad owned a brewery, and he got to play around in the brewery. And then playing around in the brewery, he made a cool connection between heat and energy. And because it wasn't very well understood, in honor of that cool discovery, the unit for work and energy is named after him. So joules, or capital J. I'm always going to be careful to write our equation with a dot instead of an X. That'll make sense when you get to grade 12 math. When we multiply vectors, there's different ways to multiply vectors. The dot is a particular way where we take two vectors, multiply them together, and we get a scalar out of it. Work and energy is not a vector. It's going to be a number in joules. The non-metric unit that you've seen before is calories. So when you go to order some food at a restaurant and they say, oh, that burger's got 20,000 calories. Well, 20,000 is a bit big, but that burger's got 2,000 calories. They wouldn't say 2,000 calories north or south or east or west. Direction for energy isn't necessary. It's just a number with its unit. So work, energy, scalar, no vector hat on it, but it's a product. We get it by multiplying the vector of force and the vector of displacement. Later in physics, we're going to learn other quantities where we take two vectors and we multiply them and we get a third vector. That's a different kind of multiplying, but we'll save that for grade 12 physics and grade 12 math. Sticking with our equation, we didn't get to this in grade 11 forces, but sometimes the force we put on an object isn't in the exact same direction that the object moves. Our force is kind of doing two things. The force is kind of lifting the objects, that's this side of this triangle, as well as dragging the object across the ground. Sorry, not coming through as good as it could. If the force is on a funny angle compared to the displacement, so the classic case of pulling your suitcase through an airport or whatever, when the force is on a funny angle, we don't consider the full force. We don't consider the hypotenuse, because that whole force wasn't involved in making it move. Some of the force, this side over here, that vertical part, was kind of lifting it, but it was this bottom part, this horizontal part, that was actually making it move. That's the part of the force that we need to consider when calculating work. I'm going to redraw it. So, that's how hard you're pulling it. That's the force. But this is really the important force that counts for how much work we do. I don't even really care about this one. In grade 12, we'll come back and talk about that. If we're pulling it on some funny angle, angle X, compared to angle X, the force we're pulling with is a hypotenuse. The side that's important is adjacent, so SOHCAHTOA, that's a cosine thing. The cosine of X equals SOHCAHTOA equals the important side. I don't know what to call that, so I'll just write out the word important, divided by the force, or the important side, the important force equals the force we're pulling with multiplied by the cosine of the angle. So in our work equals FD equation, I don't want the full F. the important force, the force I need, is the F cos x one. So a more general equation for work is it's force cos x multiplied by the displacement, or it's often written FD cos theta. Just flip the cosine term to the end. That's our general equation for work. Often when we write it that way, we get rid of the dot. And again, I'm being a little bit lazy and not putting vector hats, but it's the force, how big it is on its funny angle, multiplied by the displacement, how far this thing actually moves, multiplied by the cosine of the angle that's in between the force and the displacement. If there is no angle, then it'd be 0, and the cosine of 0 is 1, so we just turn into F times D. That's all the talking I would like to do for now. Basically, there's 3 examples there. They're different variations on finding work. And then in this last one, what I was trying to say before is, even though the last one uses the word energy, it's actually a work equation type of question. I'm going to stop the video here, but work through those 3 examples. There's video clips there so you can listen and watch them get solved. And then instead of a worksheet, I just typed a few questions on the bottom of the page, and the answers are down there as well. Have a go at work. Email if anything's bugging you, and then assuming things are good, we're going to move on. There's a check-in you got to do, and then move on to learn more about energy.